There we go. Now we're going. That's fine. Let us. I will begin with a word of prayer. Dear Father, we thank you for this day. Thank you for the students. Just ask you to be with us today. Help us to, again, Lord, glorify you in what we do, Lord. In your name I pray. Amen. All right, so we dive right into it. We say that D is a unique. D is a UFD, which means unique factorization domain if let's say if D is an integral domain, and point number one, every non-zero element of D can be written as a product of irreducibles and two, if the factorization into irreducibles is unique up to associates and reordering of the irreducible factors. Now, I have a more precise statement of that in the notes, which I'll let you look at. All right. So this is what a UFD is, a unique factorization domain. Slightly off. It's not a good sign. So that's I don't think I've ever written that on the board, so I at least owe you that much to write it on the board. So there it has been written on the board. And now the theorem. 4.8.7. And this is the so-called ascending chain condition. An ascending chain condition in a PID. All right. And it says the following. In a PID, any strictly increasing chain of ideals, let's say I1, I2, I3, dot, dot, dot. So what does it mean for it to be strictly increasing? In the sense that I1 is nested inside I2, is nested inside I3, right? Strictly increasing too, so none of these are equal. I1's not equal to I2, I2 is not equal to I3, and so forth, all right? Then here's the punchline. Any strictly increasing chain of ideals must be finite in length. In other words, there has to be a stop to it. It can't go on and on forever. All right. So I think when you first look at this theorem, it's, I don't know, to me it's kind of shocking. that we can prove something like this. And not just that, but when I show you the proof, it's actually not that long. Let's look at it. So here's the proof. Let I1 be a subset of I2, subset da-da-da, be a chain of strictly increasing ideals. In a PID, whatever. I don't really need to give it a name, right? I guess I'll call it D, though, since I called it that in the notes. Then what? What I do is I say to observe that if we let I equal to the union over n in the natural numbers of I sub n, right? So just take the union of all these ideals, all right? Then that forms an ideal. I mean, I'll pause for a second here to see if that makes sense to you. If you take something in the union of ideals, right, and you look at the difference of that, what are you looking at? Looking at the difference of things which fits inside one of those ideals. I mean, possibly more, but it certainly fits inside one of them. So it's back in the ideal again because the ideal is a subring, right, sub R and G. And Uber closure is also easy to check, right? If I take something in the union of the ideals and multiply by something outside the ring, I'm multiplying something outside, or rather multiplying something possibly outside the ideal by something inside one of those ideals, at least. Could be more, but at least one of them. And then by Uber closure of each ideal, we have that it's back in the ideal again, and hence it's in the union. It's pretty easy to check that this is an ideal, actually. So it is an ideal, but this is a PID, so what's that say? Since D is PID, which means it's a principal ideal domain, it follows what? I is equal to, it's generated by some element D, right? But, look at that, I sub I is a subset of I, which is equal to D, right? I don't care for the notes at this point. Do you agree? Do you guys agree? So this is a certainly each of the ideals is a subset of this ideal, right? The ideal I. And since we've assumed that it's a strictly increasing chain of ideals, what has to happen once you get to? I mean, what happens if this is well, these, I mean, it forces us, I'm missing some words here, guys, but that forces IN to be equal to D. In other words, I'm trying to say that the chain must terminate at I. What if it didn't? What if the chain went on past I? Then you'd have something outside the union. Like you have another ideal in this strictly increasing chain, which is somehow not in the union of everything in the increasing chain. Everything in the increasing chain. That's a contradiction, right? So everything in the increasing. This is true for all I, right? The thing is, that once we get to this one, right, we have to keep repeating it, otherwise we wouldn't have strictly increasing. I mean, let's see, I'm trying to see how to try to explain this. I mean, once we get to n, we have to stop, otherwise we would be contradicting that it's increasing chain. I'm sorry, I have somehow found a way to muddle this. I don't think there's anything to muddle, though. I'm going to go on. So theorem 4.8.8 says the following. It says that every PID is a UFD. All right? And so the proof has basically 3 steps. So let's go through it. So we'll let D be a PID with units U. So let's let U be the set of units. And then we're going to let A naught be an element of D with A naught not equal to 0 and A naught not a unit. All right? So we proceed in 3 steps. Step number 1 will show that a factorization of A naught contains at least one irreducible. All right, so let's work on that. So first of all, we're going to show factorization of A naught contains at least one irreducible. So if, let me claim. Let me put the claim here so you know what we're doing. A factorization of A naught contains at least one irreducible. So obviously, if A naught is irreducible, we're done, right? Stupid case, but true. So what if it's not irreducible? What's that mean? Yeah, else it can be factored into 2 things, of which what? So A0 can be written as A1B1, where what? Where A1 is not a unit, and B1 is not equal to 0, right? Now, if A1 is irreducible, right, then we're done, right? So what, otherwise, what would that mean? Otherwise, A1 can be reduced, right? A1 is equal to A2 B2, yeah? Where A2 is not a unit, and B2 is not equal to 0. Right? Was there a question? No? So we can continue in this fashion and define AN plus 1 not a unit and BN plus 1 not equal to 0, and have AN equal to AN plus 1 times BN plus 1. So continue in this fashion. We can set it up, right? AN is equal to AN plus 1, BN plus 1, where AN plus 1 is not an element of U, and BN plus 1 is not equal to 0. The point here is that, in fact, this gives us a ascending chain of ideals. What is that? So if you look at it, we have the ideal generated by A naught, is contained in the ideal generated by A1. Do you guys see why that is? Why are they not equal? What did we prove the other day? When are two principal ideals equal? When their generators are associates. But by assumption, you know, A1 is not a unit, so A naught and B, well, B1's also not a unit. I should emphasize. I mean, neither A1 nor B1 are units, right? I should probably say that at every level. Bn is not a unit.
Are we just, is that by our construction, or is that?
Definition of irreducible. I mean, if it's reducible, that means it can be factored into two things, neither of which are units. Yeah. So A0 and A1 are not associates, and so forth and so on. Like A2 and A1 are not associates, right? A2 and A3 are not associates, which means that, but on the other hand, this equation right here shows you that A0 is contained in the ideal generated by A1, right? And so if A0 is in the ideal generated by A1, so is everything else that's generated from A0, and so forth. So this is a subset of A2, right? So without, you know, without loss of, I mean, it has to terminate somewhere by the ascending chain condition, since we're working in a PID which satisfies the ascending chain condition. So what's that show? So suppose it terminates here, right? I think I used a K in the notes. Suppose it terminates at K. So what's that give us? That gives us A0 is equal to A1, B1, but that's equal to A1, A2, B2, equals to, equals to what? A1, A2, A3, A K minus 1, and then what's the last? I guess the last step would be what? A1, A2, A K minus 1, A K, B K, right? And does that factorization include an irreducible? Yeah.
But yeah, are we missing a B for the A's before we get to the? We have A1, A2, A3, AK.
Oh yeah, this is supposed to have B. I'm sorry. Have I neglected my? What have I done? Yeah, probably, yeah. I can't. A stupid eraser gone too. All right, so if I could actually follow my own argument, A0 is equal to A1, B1, which is equal to what? A1, what was, oh, that's A2, B2, B1, right? And so forth until we finally get to A sub k, B sub k minus 1, B2, B1. So certainly, by the algorithm, AK is irreducible. I think, in fact, most of these are irreducible if you follow the argument more. I mean, there's at least one. That's all we had to prove. All right? So that's step one. In the interest of this not taking the whole class time, I'm going to use the projector. This takes me forever and a day to write out. Ugh, grief. Come on. So each stage in the argument, I forget if the third stage or not, but the second stage also uses the ascending chain condition. So it's, I don't know, to me it's very kind of surprising that you can make these sorts of arguments, make arguments about factorizations using, nestings of ideals. I don't know. To me, it's interesting. I guess I shouldn't be too surprised by that, because after all, there is an interplay between, the ideals of Z and prime factorizations in Z, right? So it shouldn't be that surprising to me that this sort of thing works out. But here we go. So I just went through part 1 badly. Let me go through part 2 badly now. Let me make it bigger here. All right. So step 2, well, suppose, what's our next step here? Step 2, if A0 is irreducible, then we have a factoring of A0 into irreducibles. All right, great. Again, that's true. So by 1, there exists an irreducible P1 and a non-unit C1, for which A0 is P1 times C1. Now, if C1 is an irreducible, then we're done. We've factored A0 into irreducibles. The goal of step 2 is to show that we can factor anything into irreducibles. Otherwise, we apply 1 to a non-unit C1, and then that splits C1 into P2, C2, where at least P2 is an irreducible, right? And so we keep doing this. I don't know. As I look at this thing, I got this proof from, I think, Galeon's abstract algebra book, but it almost feels to me like 1 and 2 can be combined, honestly. I'm not convinced that 1 and 2 really need to be separate arguments. Maybe I'm missing something. I don't know. But anyway, however you want to slice it or dice it, definitely we have this ascending chain of ideals built from, these prime factorizations, these irreducible factorizations, rather. And as such, since we're in a PID, it has to terminate somewhere. And the fact that it terminates gives me the decomposition of this non-zero thing into a product of irreducibles. So all that remains then, so this shows existence of the factorization, right? So all that remains then is to prove that, it's unique up to associates, right? So that's step 3. Suppose that you have 2 factorizations, right, into P's and Q's. Mind your P's and Q's. And sub T and sub S. So possibly a different number, right? So the proof is by induction on T. If T equals 1, then this is equal to that, right? And if you had that, what if S was not equal to 1? What would that say? That would say that this irreducible P1 can be factored into a product of non-units, which would be troublesome, right? That would contradict that P1's irreducible. So that forces S1 to equal to 0. That's the induction step for 1. Suppose it's true. So next we suppose inductively any factorization into less than T irreducibles is unique up to associates. All right? And then, let's see here. So notice that P1, I think I'm supposed to have, less than T, right? Words matter. So I'm assuming the induction step is that the result holds up to order T minus 1. I'm using strong induction. Then I'm considering a factorization involving T irreducibles, right? And my goal is to show that these are unique up to reordering and association. So if P1 divides this product, that means that P1 must divide something in there, right? So P1 is equal to uj, qj for some unit uj. Let's see here. Why does it have to be a unit? Oh, because otherwise what? What if uj was not a unit? that would say what? That P1 could be factored into, it could be reduced, right? But P1's irreducible, so we can't do that. So that must be that Uj is a unit. And so I take my P1, I replace it with Qj Uj times all that, right? And then remember, backdrop, integral domain, we still have cancellation property, and things commute. So I can cancel off the Qj's. And then I've got Uj, P2 da PT, and Q2 da Qs, which is less than T irreducibles, right? So then by the induction step, those have to be unique up to association and reordering, which then proves that it's true for T, and so we have a UFD. Anyway, it always takes me longer to do this proof than I expect, and partly my heart's not in it sometimes because I don't feel like we do calculations like this elsewhere in the course, but it would be a shame for me not to share this with you because it's an example, maybe the first and most powerful example of where the ascending chain condition does something non-trivial for you in mathematics. This is not the last time this happens if you go on. The ascending chain condition is, it's a deep and relatively recent discovery. Like this is from like early 20th centuries, this way of thinking. This is due to Noether's school, where much of the abstract algebra that we now study is in some sense or another, at least the way we study it, due to Noether. So now, once you have that result, other things follow quickly. Since we've already proved that f of x is a PID, it follows that it's a UFD. Proving that f of x was the polynomials were a PID was easy. We just did arguments with the division, like basically looked at the set of possible degrees, proved it had a smallest element, therefore we had a generator. Like the argument wasn't that bad. And then likewise, that argument actually generalizes, in fact, every Euclidean domain is a PID. If you look at this argument, it's almost exactly what I told you already in the case of polynomials. So I encourage you to read it. You should have a strong sense of déjà vu if you believe that sort of thing. Anyway, corollary, every Euclidean domain is a UFD. So let's collect the pieces here. What do we got? Let me put this away, actually. So let's see here. What I'm just telling you is that if we have a Euclidean domain, right, that implies that you have a, what? What did I just say? A PID, right? And what did we just prove a PID? Every PID is a UFD. None of these implications are reversible, right? There exists a UFD which is not a PID. So the example of that, Zx, I believe, polynomials with integer coefficients, is an example of something which is a unique factorization domain, but this is not a PID. Right. You can find an ideal in which an ideal in there which is not principal. I think I look at the ideal generated by like 2 and x or something like that and show it's not principal. If you need two things to generate the ideal, that doesn't. Well, if you generate an ideal by two things, right, it may or may not be principal. If you generated it by two things such that those two things could actually be reached by a single thing under generation of the ring, then it would still be principal, right? But if there's no way to take the ideal generated by 2 and x and rewrite it as the ideal generated by just one thing, then it's not a principal ideal, right? And in fact, you can prove that Zx is not a PID. Now, the example of a PID which is not a Euclidean domain, I can't write down. Okay. There's a link in the notes to some examples. That's actually hard. Yeah. All right. So finally, here we are. 18 minutes left to do lecture 29. It's okay. I will catch up. I'm joking. But I will start lecture 29 at a minimum. Sorry, if I was lazier, I would just say, well, you can read the notes and not have gone through this with you. But in my heart, I know that if I do that, about half of you won't even look at it. So, so you leave me no recourse but to talk about it in here, right? I hope I'm wrong. Let me be wrong, right? Let me be wrong. I'd like to be wrong. Let me be wrong about that. Lecture 29. Okay, so this lecture is chocked full of calculations and lots of problems and ideas that make for great questions for this course and elsewhere. Anyway, so lecture 29 is on extension fields. So first things first, definition. A field E is an extension field of F if F is a subset of E and the operations of F are those of E restricted to F. There's probably a lazier way of making this definition. We call F the base field of E. All right. And there's also something else. We like to make what's called, and this is not in my notes, but it should be, but I probably, when I wrote these notes, didn't feel like figuring out how to tech this, but I should, because it kind of matters. And so here's a picture. E is the extension field, and F is the base field. So we can make this picture, tower of fields diagram, right? So what are some examples? How about we have the real numbers are an extension of the rational numbers? What have I done? Oh. You're trying to make an example of Taylor? Hey, I'll accept it. I'll allow it. I do that all the time, and that's one of my main pastimes in differential equations, actually. Like if I get bored with a calculation, I'll just stop and like make fun of Taylor. Oh, wait a minute. Example 1, right? Example 1. How was I getting to example 2? Oh, yeah, example 2. So how about the complex numbers, right? These are an extension of the real numbers in our usual. Oh, that was Taylor's example. Okay. All right, so let's make an example of both of us and combine these examples. So you could do this, right? Complexes over the reals, which are over the rationals. We can do that. So in other words, Q is extended to R is extended to C. These are extension fields. Another example, we've talked about Q adjoin the square root of 2, right? So if you look at that, that's an extension of the rationals as well, right? It's an extension of the rationals. Yep.
So is this transitive? Does that mean that C is an extension of Q?
Yes.
Yes, it's an extension of R.
Uh-huh. This is true. Yes. The extension of the extension is an extension. Hey, that's not always the case, right? With other things we talk about. For example, things being normal subgroups of other things. Like if you have a normal subgroup of a normal subgroup of a normal subgroup, is it a normal subgroup? Does my question even make sense? I'm not sure. But if you try to do like transitivity of normal subgroups, there's some wrinkles there. It works one way but not the other, and I shouldn't get into all that at the moment. We actually end up needing to get into that a lot next semester as we study Galois theory. So I'll leave it for there. Or your final, I don't know. But that was a joke. It was a joke, mostly a joke. Let's see here. An example 4 that I mentioned is this one. If you take z mod 2, adjoin x, mod the irreducible polynomial x squared plus x plus 1, how do I know that this is irreducible? How do I know that that's irreducible mod 2? How about plug in 0? What do you get? 1. Plug in 1, 3, also known as 1, right? So it's pretty easy to show that that polynomial has no zeros, mod 2. Consequently, by our theorem, it's quadratic, it has no zeros, it's irreducible. But if we take an irreducible polynomial and generate an ideal, that's a maximal ideal. Consequently, that quotient is a field. So there you go, that's a field. And that's an extension of what? If I call this thing E. Let me just erase this actually. This is an extension of Z2, of course, right? How big is that extension? Z2 has 2 things in it, right? How many things are in the extension field? 3? Well, at least 3 things. I'll go with that. Theorem. Fundamental theorem of field theory. The answer is 4. Because a typical representative in here looks like what? A plus B x bar, using my usual notation here. Letting, A plus B x bar be equal to A plus bx plus the ideal generated by x squared plus x plus 1. Yeah. So A and B are free parameters of that factor ring. They both take 2 values. You got 4 cosets. All right. Okay, fundamental theorem of field theory, also known as Kroneker's theorem. That's the same Kroneker who gave us the delta that I love so dearly. So 1887. And this theorem, it's really amazing. I don't know, I think it's amazing. Here's the deal. You give me f be a field, f of x a non-zero polynomial. And f of x in fx non-zero. Yeah, I think I need more than non-zero. I need, non-constant rather. Let's be more specific. Non-constant polynomial. All right. Then there exists an extension field E of f in which f of x has a 0. So which polynomials allow zeros? If you extend your view from the field that you're given to the extension field that you can make. Any non-constant polynomial has a 0 and an extension field. That's kind of neat, right? So apparently, this theorem says that if you can't find a 0 for a polynomial, it's just, in some sense, a problem of perspective, right? If you can expand your imagination a little bit and find the correct extension field, you have a 0 for the polynomial. So, and the proof is actually pretty easy. Let's look at it. What we're going to do is we're going to let f of x in f of x be non-constant polynomial, right? Since f adjoint x is a UFD, right? Since we proved it's a PID, and I almost proved that PID implies UFD today, so certainly polynomials are a UFD, which means what? F of x can be written as P of x times G of x, where P of x is irreducible. When's your homework due?
Monday.
Which Monday? What's today?
Wednesday.
We're okay. I lost track of what day it was. I was kind of worried for a second. I thought I had to push the homework back, but nah, we're okay. You're like, rethink your thoughts. You can always push things. You guys always want me to push things back. It's here. Where was I? Okay, so P of x is irreducible, right? Let E equal to f of x mod the ideal generated by P of x. This is a field. Since P of x irreducible implies that the ideal generated by P of x maximal implies that f of x mod the ideal generated by P of x is field. Right? So, let alpha equal to x plus the ideal generated by P of x. Okay? I'm going to argue that alpha, as defined, is a 0 for f of x. Well, I'm actually going to define. I'm going to show that it's a 0 for P of x. But then if it's a 0 for, if we can prove that it's a 0 for P of x, it follows it's also a 0 for f of x, right? So why is alpha a 0 for P of x? Well, what's P of alpha equal to? So at this point, I guess I need to give you the details of P of x. So P of x has to be equal to something like a0 plus a1x plus plus an x to the n, right? Where a0, a1, an are elements of where? The field, right? So what do we mean? What do we mean by P of alpha? What this means, of course, is that we're looking at the. I want to look at the evaluation homomorphism, right? Phi alpha of P of x is what I'm doing, right? Going back to that notation we introduced. So I'm going to replace, and it's a little bit, there's a little bit more going on, because I am, well, let me just write it down here. So I'm saying that that's A0 plus, there's an abuse that I'm making here, but I'll try to elaborate on that as we go here. A2 alpha squared, an alpha to the n, which is actually what? So by that I mean A0 plus A1 times x plus the ideal generated by P of x. Oh man, I'm going to get tired of writing that pretty soon. Plus A2 times x plus the ideal generated by P of x squared. But how do we, when you square something, what do you do? Will you guys allow me a slight cheat here? So what I'm going to do is I'm going to put that 2 over here, put that n over here if that's okay. I mean, that's how we power a coset, right? But then how do you add these? Well, you've got A0 plus A1x plus A2x squared plus plus ANXN, that plus P of x, right? But what is that? That is P of x. And so what is this? This is all P of x, which is also known as what? 0 bar, right? So here's the fast one I'm trying to pull on you right now, is if you want to be fussy, right? And sometimes we do, right? Is F a subset of E? I mean, in some sense, yes, but I mean, in some sense, no. and here's what I mean. So here's the question. If I have C in this field, right? What's the C over here? We're trading C for C plus the ideal generated by P of x, right? In other words, we're trading C for C bar. So if you're willing to identify the constant with the coset labeled by that same constant, and there is a one-to-one correspondence here, then we do have a copy of the field inside the factor ring. Okay. Now, this identification is made all the time without comment. In some sense, we're doing it even in like real numbers, right? Like in principle, you could say, well, A versus A plus I times 0 are different things. Like, this is a real number. If you're building the complex numbers as a factor ring, this is A plus the ideal generated by x squared plus 1. Right? But we'd like to think of A and A plus I times 0 as being the same thing. The abuse of that is the identification of the constant with the coset represented by the constant. Now, if you're willing to make that abuse, this theorem holds directly, right? Now, the other way to fix this would be to go back and say, you know what? E is an extension field of F if F prime is a subset of E, and the operations of F prime are those of E restricted to F prime, blah, 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 where F is isomorphic to F prime. You could fix it at the level of the definition. Just say, you know what? We're going to talk about extension fields up to isomorphism. I mean, that's what's done. Sorry, I don't mean to end class on such a confusing note. This theorem is really quite something. Isn't that too simple? You just essentially take the polynomial you're interested in finding the 0 for, pick any irreducible factor you like in it, form the field by modding by that, and in that quotient field, I mean in that quotient ring, there's a 0, where the x is the 0. It's kind of cool. All right, enough. I will stop. Much more of this next time. Oh, and I also have homeworks, apparently.